All right, great. Yeah. So I'm Gautam. I'm a software engineer at Google. Probably just to remind you from last lecture, but this time I'm going to go over um, techniques related to data visualization. And data visualization can help us communicate our findings or our data sets to people, but it can also impart a lot of understanding and it can enable us to have intuition on what types of techniques we want to use to model data and also understand certain types of patterns in data that might not be readily relevant or they might not we might not be able to understand them because the dimensionality of the data is so high. And these are two examples. On the left, and I put links here if you want to go explore them in more depth, but on the left is an example of eating habits in different regions of the UK. And it's a 17-dimensional data set. And by looking at it, it kind of looks like everyone has the same pattern. And it's really hard to understand differences between the different regions. You could try to say, okay, let's plot it into a 17-dimensional space, but then it's really difficult for a human to understand what that means, and we can't visualize it either, where we're looking at all 17 dimensions at the same time. Another example right here is facial expressions. If we want to understand the relationship between facial expressions, there might be 50 types of facial expressions. And we want to understand the relationships between them. And it's not readily apparent. How do we take these facial expressions and somehow visualize them in a way that separates those distinct expressions without having labels beforehand? Is there a way that we can put it in a two-dimensional or three-dimensional space so that we can make conclusions about it? And also feel free to stop me with any questions. And so here are some solutions, which I will go over a bit more in the lecture. But on the left is an example where we have images of digits. And so you can think of one of these images as having 1,000 pixels and residing in a 1,000-dimensional space. But we want to understand the structure of this space. And one way to do that is to project it into a three-dimensional space where we can actually see it and make judgments about it. And in this case, you can see that each of these clusters represents a separate and distinct digit. And on the right is actually a paper we worked on at Google where we use a technique called t-SNE to project the range of facial expressions around the world onto a two-dimensional space so you can understand how each of them relates to each one another and how separate they are. One of the most common techniques for visualization that you'll often see in the literature is principal components analysis. And this is a linear technique applied to data, oftentimes to reduce the dimensionality, but also to come up with visualizations in a much lower dimensional space and to simplify it into the most basic components. And I'll go over some of the intuition about it and where you might want to use it. But I provided some links to a Python library with an implementation and with all of the gory mathematical details. It actually builds off of what we talked about last time, where before you feed in data into the principal components algorithm, you need to normalize it in a certain way for it to work properly. But I'll try to give you a high level understanding of what it's actually doing. And there's also a site that has these amazing visuals that I've recreated here to try to walk through what PCA is actually doing. On the left here, we have two-dimensional data. So each of these data points has a value on the X and Y axes, and they're plotted in this two-dimensional plane. And the whole idea of PCA is you want to take those two axes, like your X and your Y axes, and rotate them in some way such that the axes are lined up with the highest amount of variation in your data set. And to give you a bit more detail about what that means, if on the left, if you look at your data superimposed on the X and Y axis, you can see that it's sort of spread evenly across those two axes, meaning the X components of each data point are spread around like 2.3 to 8.1. Same with the Y, there's sort of a equal spread around them. And the goal of PCA is actually to come up with an ordered set of new axes based on this rotation, such that the first dimension encompasses the most amount of variation in your data set, and then the last dimension represents the least amount. And so on the right here, we've actually lined up our data with these new PCA axes, and you can see that the first of these is component PC1, and it actually represents the direction of most variation in the data. And so what you can do is look at how the data is projected onto that axis, and you can see that there's a huge amount of variation from like -3 to 3. While in the second dimension, there's very little variation. It's almost all centered around 1. And so one of the conclusions you can make here is that all of the rich information found in this two-dimensional data set can actually be represented in 1 dimension. Basically, all the differences and changes happen in that 1 dimension. And the second dimension isn't really that useful. You can basically describe it in 1 dimension. And that helps with subsequent computations because now you only have 1-dimensional data. And it helps for you to understand it better. You can try to track the changes in this data set by focusing on that one specific dimension. And then we can scale it up to give you a better understanding. So on the left, the first column is 3-dimensional data points. And they're in this standard space. You can, like PCA1 and PCA2 in this top row, you can think of those as the X and Y of the last plot. And so they're just standard coordinate system, and then you plot your data, and then you can project it onto the X, Y, and Z axes, like at the top right in the third column. And you can see that there's like sort of an even spread there. But then what we can do is we can feed all of this data into this PCA algorithm, and then we get new axes. So on the bottom left, you can see that now the axes are lined up with the most the largest amount of variation in your data set. And then in the middle of the bottom row, you can see the 2D projection of that, where the green axes, the red axis is going through the highest amount of variation. And then on the bottom right, you can see, like, let's project the data back onto those 3 components. And you can see that there's one component, PC1, that represent the highest amount of variation. So in some ways, you could almost argue that in this data set, maybe instead of 3 dimensions, we could represent it as 1 dimension to get an understanding of where variation is happening in this data set. And one application you could think of is if you want to train some kind of machine learning algorithm to classify something, and you have data points that reside in 100-dimensional space, there could be a situation where you feed all that into PCA, and then it comes out that there's only one axis that represents all of the variation in your data set. And because of that, when you run your algorithm, it could run a lot faster because you're just running it on 1 dimension. And then you can also display it and show it to people to better understand, like, what is the pattern in this data set that actually matters, as opposed to having 99 dimensions that really don't play a large role.
So there was a question in the chat. In the previous graph, is the low variation related to the linear relation between the 2 data?
The low variation in the PCA dimensions, I need to
Yeah,
ask.
maybe. Yeah, could you follow up to the person that, yeah, whoever wrote the question? If you want, feel free to like follow up, or if you want, I can unmute you if you want to ask the question. Maybe I'll do that. So you can unmute yourself. Yeah, go
Thank
for it.
you. Am I hearable now?
Yeah, we can hear you.
Yeah, I just mean like in the original data set, it seems like there's a linear relationship between X and Y. And so it's almost a line and you can like tilt that line. That's my understanding.
Yeah. That's
Is that
actually a
right?
really good point. Yeah. So there is a linear, yeah. So like PCA is a linear method because we have these axes aligned to the data and we're purely just rotating it. And because there's a very specific type of linear relationship in the data, that's why PCA is working so well here. That's a really good point to bring up, and that sort of feeds into like the t-SNE discussion that I'll talk about later. But one assumption is that in many cases, you need to have some kind of linear relationship in your data for PCA to work. I mean, it's not like true for everything, but oftentimes, like if it was some kind of weird curve, we wouldn't be able to rotate those axes to be able to line up in the direction of the most variation. And because, yeah, that's a great point that you pointed out, that there's like basically a line, we can rotate everything to fit that line and match that amount of variation. And same with like the 3D example, there's sort of, you can sort of think of, there's a line that you can fit to this 3D data that represents the most amount of variation. And those are really clear to see in 2D and 3D, or 3D and 2D spaces.
Yeah, one of the counterexamples I always like to use is if I had a bunch of, actually it doesn't work with that. Let me clear that. Let me use a stamp so I can just click. So if I had a bunch of points that were like this, distance from some origin point could cleanly separate them if I transformed it into a space that was like distance, but PCA wouldn't be able to necessarily detect that because there's no way of rotating. Actually, could it? Wait, maybe it would work on that. No, I don't think it would work on that because it would be a quadratic space. It wouldn't be a linear rotation.
Yeah, you'd need to transform those points into like another space that was linear, project them into a higher dimensional space that was linear or something, or another.
Exactly, yeah.
I mean, one big advantage of PCA is that it's very quick to compute on large amounts of data. And like if you look into the literature, there are these complex matrix operations that you have to do, but there's numerical solutions to that. There's a way to do it where you can batch PCA, where you just start doing it on parts of the data and you have really gigantic data sets. Which is a really nice feature because a lot of the nonlinear techniques that can handle like the circular pattern that Nima showed are a lot slower. And then I'll try to go back to that original example. Like, let's say when we have these 17 different attributes of how people eat in these different regions of the UK. Initially, it's really hard to tell if there's any significant differences between them, and like which of the components do we look at. There's so many different variables here. Like, do we just focus on alcoholic drinks, or do we focus on cereals? Like, how do we understand if these regions are significantly different in their eating habits? And so what you can do is you can run all of that data into PCA. So on the top here is the first component of PCA, and it's projected all of those different regions onto that axis. And so the reason why this is really helpful is you can think of this whole data set. So there's 4 different regions, and they're actually points in a 17-dimensional space. And it's really difficult to understand, like, what does that mean when we look at that? But what PCA allows us to do is project them all into a direction that represents the highest amount of variation in your data set. And so by looking at that first PC1 component, we can see that there's a huge difference between Northern Ireland and these 3 different regions. And what's really nice is that this dimension in the data set, it could be like, in some instances, maybe it means one thing, like it could just mean confectionery. But in this situation, it doesn't. It's some kind of complex linear combination of all of these factors here that really show you that there is a significant difference between these regions. And you can go one step further and then plot it on the top two different PCA directions. So PC1, we already know there's a huge variation. But then if you look at PC2, there's actually not a huge variation between those 4 different regions. So it shows that there's just basically one component that represents the difference between these. So it's not as complex of a story here, but it is a really nice way to help us understand this data visually without having any ground truth saying how these countries are different. And if you read up on the example here, one of the differences they point out is that Northern Ireland is actually not like contiguous with the other regions, like it's separated by water. And maybe that contributes to why the eating habits are different. Now I'll talk about a method called TSNE, or like distributed stochastic neighbor embedding. And one like the question that was asked, one really big advantage of this is it's nonlinear. It can represent much more complex patterns in your data. And there's some trade-offs with that. But I'll try to give you a high-level intuition for what it's doing. It's the formal definition encompasses a lot of like statistical methods, comparing probability distributions. But at a high level, let's look like at this example, where on the left, we have a bunch of images, and we want to understand the relationship of these images to one another in a space that our brains can comprehend. So on the right are 2D representations of the relationship between these images. And on A, we can see the visualization from TSNE, where there are these very tight clusters that represent certain subtypes of these objects. Because there's a really complex pattern that separates like a can of Vaseline with a toy car. Whereas a lot of the other common visualization techniques, it's very difficult to understand the difference. They might actually separate them, but for our brains to look at a 2D representation like the one from ISOMAP, it's very difficult to understand the different categories. But at a high level, what TSNE is doing is it is looking at the relationships between these objects in their basic space. So if, for example, let's say these images were like 100 by 100. And so all of those pixels like represent a large space that each of these images reside in. And what TSNE will do is it will look at each of these images and understand the relationship to their neighborhoods. And it'll model this probabilistically. And then it will try to create a low dimensional representation of the relationships between these images that keeps the constraints that their neighborhoods are very similar. And so what that means is like the local relationships it tries to preserve the local relationships in a low dimensional space. So for example, in a high dimensional space, let's say this was like 1,000 dimensional space where each of the images, we calculated some distance between them. And so maybe like images of toy ducks were pretty close, and a duck and a car were very far from one another. What it tries to do is in the low dimensional space is make sure that like ducks are relatively similar, and it doesn't actually put any constraints like global constraints on this space. And because of that, it can create these very complex patterns at a very local level and allow us to visualize very complicated relationships that PCA wouldn't, which requires like oftentimes a linear relationship. And I'll give you a few more examples for what this means. So this is a really common data set used in machine learning called MNIST. And it's a bunch of hand-drawn numbers. On the left is a sample of the data set, and on the right is a zoomed in version where you can see the different pixels. And this resides, let's say, in a 1,000-dimensional space, each of these images. And so one thing we could do is use this as an example for how do we understand the differences showcased in this data set. For us, we know their numbers, and so we expect there to be 10 different clusters representing each of these digits. But we could think of maybe this was a more complex phenomena. Maybe it was some kind of image of cells or some other kind of like biological phenomena that we actually didn't know the clusters beforehand. And we wanted to visualize it in a way that showcases that. And so what we've talked about before is we could try to use PCA for this. So on the left is a PCA visualization of it, where we projected that 1,000 dimensional space into a 2-dimensional space. And each of these colors on the left represent like the digit. So like red could be the digit 4, gold could be the digit like 7. And you can see that in PCA, there's sort of a blob. It's really hard to understand if there's any structure to this space. And the reason why is that these shapes are, the relationship between these image shapes and the pixels on them is very complex, and it's a nonlinear relationship. And PCA it doesn't have the complexity in the model to be able to put that kind of structure in a low dimensional space. While with TSNE, it's able to model those nonlinear effects, and it actually just looks locally, saying like, let's look at the number 3. What are the other points in the high dimensional space that look like the number 3? And it's able to project that into the low dimensional space and give you a representation that pretty readily separates all of the numbers from one another. I'll do another example. Let's see. There are a few really cool examples that actually Google has done. So this is a huge TSNE plot for artworks. And I'll see if I can, let's see if I can change the tab so I can like explore it. Okay. One second. Okay, are you able to see this visualization?
Yep, perfect.
Okay, awesome. So like, in essence, this is like so many, what this is doing is trying to show the relationships between like thousands of artworks from all over the world. And one thing is just the sheer number of values. It's hard for our minds to be able to make any sense of it. But the second thing is that we want to understand, are there coherent like clusters in this data set? So you can see here, like this is a huge, like, I'll try to zoom in so you can look at it better, but this is like a huge distribution of images from all different categories of art. And you can make out there's like small little clusters, and I will do this guided tour so that we can like zoom in on to certain parts of it. So we could look at like this section right here. That represents like a certain type of art. Let's see if I can zoom in. Yeah, so this is like a certain type of painting that's called Japanese wood blocks. And the TSNE method was actually able to let's see, automatically cluster all of this type of artwork together. And so what's really nice is you can feed all of these artworks into the algorithm, and it will automatically be able to push them all together purely based on the relationship these artworks have with one another. Let's see, let's go to another one. And you, like, I put a link where you can play around with it. And what's really nice is, like, once the t-SNE plot is there, as a human, you can go in and try to understand and interpret what the patterns and the clusters mean. And for our work, it can be pretty simple. You can say, like, okay, all these paintings seem to have gold in them, and that's why t-SNE is working. I'll do another one to show you. This is another Google project, actually. Hold on. Okay, so this is another t-SNE plot where different types of art were annotated with the emotion that it evoked. And so if you, let's see, like, I'll highlight work of art. So, like, for example, like striking could be emotion, or like lively, vibrant could be another emotion that's evoked by it. And so what this allows you to do is, like, click on an artwork that matches that type of annotation, but it also is a pretty nice way to understand how artworks relate to one another. So you could look at, like, between tense and anxiety and mysterious. That's a really complicated set of relationships. And then you can kind of look at artwork that sort of exhibits those really, like, high level human like ideas. Or you could look at, like, something at the border of boredom or brooding dreary. And so something like that is really difficult to represent because it represents a bunch of different human ideas in a high dimensional space, but we can use t-SNE to just map it into a two-dimensional space that you can play around with. Okay, I'll go back to the slides. Okay, are you able to see the slides again?
Yeah, it's not in presenter mode, but
Okay, yeah, all that in, thanks.
yeah, no problem.
Okay,
Yep.
yeah, so I'll give, like, a final summary of both of these methods. So I talked about PCA, which is a linear technique. There's a bunch of implementations online that are really fast if you want to use them on your data. They allow you to come up with really concise understanding of the, like, deep relationships found in your data, and also to reduce the dimensionality for any subsequent processing. And maybe you use PCA and you find that you're not able to make any sense of your data set. Another more complex technique is t-SNE. So, I mean, like, in practice, typically you would start with something more simple like PCA and then move to t-SNE. where you can try to surface more complex nonlinear relationships with your data. And another thing with t-SNE is that it can be very slow when the dimensionality of your data set is very high, and it can be very sensitive to different parameters. So I put a link actually in the slides that goes through an article about all the caveats of the representations that you come up with and what types of conclusions you can make from them. But in both cases, when you're working with a data set, these are a really good way to make sure that the data makes sense before you do any processing on it, and also to understand whether you can actually simplify your problem into something that's really like a one-dimensional problem or a two-dimensional problem, and identify like a very simple relationship before trying to feed in much more heavyweight tools from machine learning like neural networks or something.
So there was a question in the chat. It looks like both projects are towards art, but one is more art style versus one is more related to emotion. Are these differences because of the dimensions decided by the researchers, or is the dimension still just pixels?
Oh, yeah, that's a really good question. So actually the emotion work for each of those artworks, humans annotated them with like the emotions that they evoked when they looked at that art. And so, for example, every artwork might have 20 answers. And these reside in like some 20-dimensional space that represent each of those categories. I can go back to that slide. Yeah, or like, okay, maybe it's 40 dimensions that, so like everyone says like, does this painting give me nostalgia? Or does this like evoke awe in me? And so you can think of each of those words being embedded in like a long vector. And they represent some 20-dimensional vector for each of these artworks. And then we want to say like, okay, what is the relationship between all these artworks given the ratings that humans gave in this like 20-dimensional space? And what t-SNE does is it allows us to embed that information in a 2D space. So in this example, it is very different because it's actually not the pixels. It's really like the human ratings that were applied to each of those artworks. And these are kind of just like fun examples that you can go through and explore, and it's readily interpretable what it means.